Now, in contrast to that number, though, let's compute another one. Let's compute what happens if the process mean changes. I'm going to have to say how much the process mean changes. I'm doing a what if calculation here, so I can make any choice I want. For sake of illustration, let's suppose that what I'd like to do is know what happens if the process mean changes by one process standard deviation. But sigma stays unchanged. The idea is that that's not a good circumstance. Something has changed in the process. We would hope that the control charting scheme would tell us about that, and hopefully what that's going to mean is that we get an average run length that is not 370, but is smaller than 370. So we hope for a small ARL under this circumstance. Well, okay, exactly what do I need then? Well, here's the right picture. There's the lower control limit for X bar. It's at the original mean minus 3 sigma over the square root of 5. There is the upper control limit for X bar. That's at the original mean plus 3 process standard deviations over the square root of 5. And here is the original mean. But I want to change things up by saying that the actual process mean is not the one used to set the chart up, but is changed to mean plus 1 process standard deviation. Okay, so the idea is that I don't have that picture that I drew earlier for X bar, but rather I have a picture that looks like this. So this is the distribution for X bar. It's not centered at mu, but it's centered at mu plus sigma. It still has standard deviation sigma over root 5, but now the value of Q that I'm facing is this plus that. And that value of Q is going to be bigger than my earlier value of Q. So let's see how that goes. And say that here Q is going to be what? Well, it's going to be the probability that X bar is less than the lower control limit plus the probability that X bar is, for the first sample, is bigger than the upper control limit. And this is still mu plus 3 sigma over the square root of 5. This is still, sorry, this is not plus, this is minus. This is mu plus 3 sigma over the square root of 5. But now, in order to turn this into a standard normal calculation, what I've got to do is to subtract not mu, but mu plus sigma, because my picture is this picture down here at the bottom, where I've got the distribution of x bar not centered at mu, but centered over here at mu plus sigma. So, for example, this guy right here is the probability that x bar minus mu plus sigma is less than mu minus 3 sigma over square root of 5. That minus mu plus sigma. So I've subtracted a mean. I'll now divide by the standard deviation for x bar, which is sigma over the square root of 5. And sort of magically here, this guy is now somebody that I'll call a standard normal variable. Why? Because I've taken a sample average, I've subtracted its new hypothetical mean here, and I've divided by its standard deviation. And if I do the arithmetic or the algebra on the right side, the mu's go away, they cancel out, the sigmas cancel out, and I just wind up with a number on the right hand side. And that number turns out to be minus 5.24. If I do the corresponding calculation on the right side, what I wind up with is a probability that a standard normal variable is bigger than, well, as it turns out, that's 0.76. And so what I want finally here for my value of little q is a probability that a standard normal variable is less than minus 5.24 plus the probability that a standard normal variable is bigger than 0.76, and that turns out to be 0.2236. And now the average run length is the reciprocal of that, and that is on the order of 4.5. Okay, and the point is, it will take, on average, 4.5 periods to detect then a change in process mean from mu to, say, mu plus 1 standard deviation using a Shewhart X-bar chart with a sample size of 5. My point is that this thing is a quantification of what to expect if I use this X-bar chart with a sample size of 5. If everything's okay, I have about 370 periods on average between false alarms. If things change to where the process mean is not at the center of the at the midpoint of the between the control limits. It's not at where I set things up to be when I started doing X-bar charting, but rather changes to mu plus sigma. Then I detect that reasonably quickly, in the sense that it takes me on average 4.5 periods. Now you can play this kind of ARL calculation game with any distribution for which you know how to compute probabilities for Q's.